Welcome back to Manufacturing Roundtable. I'm your host, Eric Ciampoli. Today I'm joined by Bill Chesterson, the co-founder and CEO of Advent Design Corporation. Bill has been building automation systems and leading engineering teams for over 30 years. His work brings robotics, vision systems, and product development to help manufacturers improve performance and bring new ideas to life and control manufacturing costs. I hope you find this conversation useful. Let's jump in. Hello, everyone. Thank you for joining us today. I'm Eric Ciampoli, the podcast host of the Lean Leadership Roundtable. Today, we have Bill Chesterson here from Advent Design. He's joined us today for a bunch of Q&A on automation and how it's affecting our global marketplace, particularly manufacturing. So, Bill, how did Advent Design get started? And what problem were you trying to solve at the time?
Well, so we got started. The problem we were trying to solve was helping companies put robots to work, which is pretty much what we're still trying to do today. I started my career in the robot design business for a company that was in the robot business, and they relatively quickly in the U.S. there were a lot of companies jumped in and jumped right back out. The one I was with jumped right back out, and so I found myself with a basic understanding of how robots work and how they're used in manufacturing, and decided to start my own company with a good friend of mine, and that's what we started doing.
Amazing. I can contest. It's not easy to start a business from scratch with not a lot of bandwidth. And so, Bill, what originally drew you into the automation and systems engineering world? What was that driver? Was it a personal passion, a hobby, just a fascination with robots?
It was a fascination with robots. When I graduated from college, there were a lot of different companies I interviewed with and opportunities I looked at, and the robot business was new at the time, and it looked exciting, and there was a lot to learn. So it was something that I was drawn to, and manufacturing has always been something interesting to me, and that's partly because there's a lot to manufacturing and understanding how it's done that's not intuitive.
Yeah, and just because they have automation, you still have an enormous human interface factor to anything you're trying to automate, because robots still need people to make them go, and they need instructions from people, and they still need interaction support. It's not completely autonomous yet, right? So looking back at some early projects and your early learnings, what shaped your perspectives on the manufacturing challenges and how automation can help or sometimes even hinder the way the organization behaves?
So there's quite a few aspects to that, and I think one, there's a few I think that I'll comment on relative to your question. When you get involved with developing an automated system, there's things that it needs to do that people used to do, and it's very hard to truly interpret how people were really doing it, even if you ask somebody. And so there's a lot that you have to figure out the hard way to get a machine to do what a human used to do, and understanding that challenge is in front of you when you get to making the machine work is probably the most important part of learning how to design automate custom systems in manufacturing. Because what you end up finding is that 90 to 95% of what you thought was going to happen happens if you're really good. And that other 5 to 10%, you have to be able to modify or change or tune or reprogram the system to make it do what it really needs to do once you figure that out. And so the more flexible you make the system to be able to go through that tuning and adjustment process, the quicker you'll get something from your floor to the customer's floor to production. And so flexibility in design to make it do what it needs to do and not what you think it needs to do right now is probably the biggest key in designing an effective system.
Yeah, a lot of conversations I'm having now about, future plans for expansion and capacity, not just automation. I'm like, okay, all the things we're talking about today, I get it. You want to go 4x, 10x, whatever that is. But what does the next 10 years look like? Because we need to think about that. Well, I'm not there yet. But if you're going to spend millions of dollars on doing something, you need to think about what else might I need to do in the next 90 days. Because the day we turn this machine on and a customer calls and say, hey, can you make this too? And you go, oh, I didn't accommodate for that.
It just happened. I mean, we just shipped this machine and they put it on the floor. They've had it a week. And their first question was, how do we expand the inventory storage in it? And it was like,
Didn't we have this conversation 3 years ago?
exactly. Somebody, it never came up as a potential need. And now it's like, well, and now the constraints that already exist because of the existing machine design that's there hinder your ability to bend what you've got to what you want.
Yep, you can only go so far. There's only so much flexibility you can design for. Or like the sweet spot. You can have this range. Everything in or out of that range, you get bad again. It's a sweet spot. Where do you want the sweet spot? Because I can't do it all.
That's right. That's right.
So, Bill, what kinds of automation challenges are your clients most often trying to solve? What's that high energy, high interest, high focus right now?
So the projects we typically get involved with a lot of times involve automated assembly. That's kind of our niche. So we get involved with, and that's when you're really get involved with the product. And so that's where the creativity and uniqueness of the machine and the application come in. When you're doing things like palletizing, where boxes are boxes, pallet patterns change, size of boxes change, but the requirements of the system and the actual process it's pretty similar application to application. That's not typically the kind of automation projects we get involved with. It's when you're trying to put together these unique pieces and glue them in a unique way, and there's so many different assembly processes: riveting, screw driving, ultrasonic welding, adhesives and gluing of all sorts of styles that create unique challenges and process understanding that we're typically dealing with. So, when you get to assembling something at a certain volume, once you get over a couple million pieces a year or whatever that number is, and those numbers come down as automation gets more flexible, you're in a position where you really can't have people putting that together cost effectively in the United States. And you really have to look at automation, and that's where we are seeing more people who are obviously looking to reshore things. And when you start thinking about reshoring things that you've sent to a low cost country, you really have to be looking at automation. And there's two trends. We're seeing that trend. The cost of having people do things gets more expensive. The cost of complex automation tools keeps coming down, and that inflection point happens at a different spot for every company, depending upon the application and what you're trying to do. But we're continually lowering that inflection point, the cost of that inflection point, that makes more and more processes automatable for a reasonable cost.
Yes, and as a fundamentals for design for manufacturing and automation come in, and I've seen this most profoundly in my circles in the cosmetics world. Just because you can form a box and put something in a box by hand doesn't mean a machine can do it. You need to have different considerations for how that box is going to break, how it's going to open, and the tab can't be that tight because the robot's going to crush it 1,000 times a minute. So be careful with what you put, and we need to change the box. You ready? It's like, yeah, but I can do this by hand. Not with a robot.
Good for you. Yeah. No, it doesn't work with a machine. Yeah.
Yeah. So, Bill, how do you, along the lines of that statement, how do you determine whether a process is a good fit for custom automation with those inflection points that you're talking about?
So we start when a customer comes to us with an application, the first thing we look at is not how to do it, but how much it's going to cost to do it, because that's really the first hurdle. Have you reached that inflection point? Is it going to be cost effective? Is it going to be within a budget range? We're only talking ranges. That I think that gives me the ROI I'm looking for. That's the first thing we do. And then if if we agree that we're in that range, then the second thing we need to do is look at the different steps of the process that we want to automate, volumes, all that stuff, and decide whether there's pieces of it that we may have an engineering challenge around. And if there's pieces of it where there's an engineering challenge or there's engineering uncertainty or engineering risk, then we look at ways of de-risking that. How can we engineer this, prototype it, do some cheap testing, do something to make sure that that we don't commit the ultimate cardinal sin, which is building a machine that doesn't work, because that's the ultimate cardinal sin. You spent all the money and all the time and all the heartache, and if it doesn't work, so we don't do that. That's what we're so careful about, is making sure, not only for us, a win is when when it really works, the customer's happy. Not, it sort of worked, we had to make compromises, we got it to do something that's useful, but it's not what the original goals were. No. You need to hit those original goals. So that's the only way you get the next job. And in our business, recurring customers are that's our lifeblood. It's not just bread and butter, that's our lifeblood. Because it's very hard for a company who's going to do something as unique and complex as what we do with someone without feeling that trust that they're going to deliver something that works. And it's very hard to build that trust. It takes small steps, it takes time, it takes interaction. And once you build that trust and you've had that interaction, you've built that trust, you've shown results, then you can take on more and more challenges, and the customer's willing to work with you. And so you don't want to do something to break that trust, i.e., deliver something that didn't succeed.
I get comments all the time like, isn't there a robot that can do stuff like this? I'm like, there is, but there's a learning curve to developing that, because just because a person can do it doesn't mean you can automate it even the same way. I say, well, what if let's take first step. What do we take a mundane, repetitive, not so fun to do task, take that away from the operator, let a automation element do that, and let the humans interface with the rest of it that's really hard to do. I can get someone more productive for less money than doing full automation, get you your bang for the buck. It gets a person involved and it makes them far more productive, which means the unit cost goes down and we don't have to solve a sometimes very, very difficult thing to solve, is how to hold something in the manner to get it into the slot that a human can do without any effort. Robots don't work the same way. And oh, by the way, that hole is variable. And the robot can't predict that the same way a person can. Oh, I'll just slide it a different way. Or I'll get a bigger hammer and it goes in. It doesn't work like that with automation. It has to be repeatable. And a lot of products I deal with, they're not 100% repeatable. They intend to be, but there's variations. So can you share a specific story of automation that delivered a surprising improvement or even an incredible lesson learned or insight?
So we've done a bunch of automation around guitar assembly and routing. So if you've got a guitar neck and a guitar body and you're trying to join them together, for example, we built a system that would CMM probe all the different points around the joints on the guitar body and the guitar neck. This is one of the last steps to the assembly process. And then we would take that information, understand angular offsets and things, and then adjust 4 different routing cutters to route that joint so that the 2 pieces would fit together, and when you string them up, the string would be the right distance from the frets. Okay, that's the key. So that was a very sophisticated routing system that we did for guitar assembly. So the next challenge was to machine the braces that are mounted to the front face of the back of the front face of the guitar. And we looked at that process, and right now it's done by hand with a chisel. Somebody uses a chisel to shape these braces so they're the right shape, and then sands them by hand in order to make it to the next assembly step of the guitar. So they wanted us to build an automated routing system that would route these braces into the right shape. And so we're thinking, okay, we have these things sticking up and we'll mill them with a milling cutter like we've done all the other guitar routing process steps that we've automated. And we started, we decided to do some testing. And what we found is that in order to use a milling cutter style router to route the top surface of the brace, um, which was before chiseled, okay, in order to route it, you had to, because of the type of wood they were using, you had to go so slow that we were about, instead of processing a guitar every 2 or 3 minutes, it was going to take us 13 minutes because we had to move the cutter so slow with all the different, in order to have it not splinter. So we had never had a splintering problem with any of the other work we've done. And now we did an initial quick test on our milling machine, and found out that unless we were going 5 inches a minute, we ended up with splintering, and we needed to go 50. And we were like, oh no. And fortunately, we were at the beginning of the project, and we discovered this early. We didn't build the machine and then start using it and find out we were at 13-minute takt time instead of 3. So we looked at the process and we started experimenting with different types of cutters that would cut in different orientations, and found that if you cut it like you chiseled it, with a cutter that goes this way instead of a cutter that goes this way, and you ran it fast enough that you could go and mill at the milling speeds we needed to go and still make the takt time. But we had to design a custom router head that, instead of using a standard router head, because all standard router heads are like a milling head. They have a cutter that's vertical that turns this way to do their cutting. But we had to turn this way. So we had to come up with a custom design. We ended up building one, testing it, and it worked. We mounted the whole assembly to our milling machine, machined a whole bunch of. We machined a statistically significant sample of braces in order to make sure that that we didn't chip wood. Because once you glue these things to the back of the guitar frame, guitar face, think about all the value that's in that right now. And if you chip it out, you've got to throw it away. You can't even take these off and replace them. So it had to be a highly reliable process. So we went through that whole process of proving that out before we said, okay, this works. This is our machine takt time. This is our design. Now let's build a machine around it.
And these are the idiosyncrasies that people have originally. So, well, a machine could just do this like a person. Not necessarily like you may think with existing methodologies and modalities. You have to invent something in order to solve the problem, to automate it. That's profound. That is quite above and beyond to make sure the product works really good.
Yeah, and it again, it's something, if once you find an issue, you've got to figure out a good way around it. Anymore, one of the things we learned is you try not to take risks, because what you're building doesn't just have to work once or work okay. It's got to work in a manufacturing environment for 20 years. So there's a lot there's a lot that has to work well, and so it's a very demanding. It's one of the most putting something in space is demanding too. All right, so there's other demanding environments, but working on the manufacturing floor is a very demanding environment.
Yeah, and unlike putting something in space, you're building one and you can test it, and then you can approve it. In automation, you're repeating this cycle 1 million, 2 million, 10 million times a year, and it needs to be repeatable beyond Six Sigma. So, Bill, what types of rules right now are you dealing with where vision systems are playing a role in the solutions that you're applying?
We use vision systems a lot. I would say most machines have vision involved. And a lot of the early robot work we did was vision guided. So we've starting 25 years ago, did an application where integrating vision with robot motion was critical to the process. So the robot was doing so what it was doing was assembling these ceramic windows into this big aluminum frame, into little cutouts. This is for the Aegis radar antenna that goes on ships. Okay, and the we were gluing these windows and putting them in these pockets, and the clearance between the part and the pocket was about 5,000. So you had 5,000ths of an inch for this square edge thing to go into this square edged hole. So and the radar antenna is about 12 feet by 12 feet. So you weren't going to dead reckon your location for any of this. So all of it had to be vision guided. And this was 25 years ago we did it. So it was early 6-axis robot, early vision systems, make them work together and use that in order to be able to do assembly at an accuracy level that you could never do any other way without vision, without some sort of sensing way to sense where stuff is in the environment and then have the robot react to it. So early on, we became comfortable with applications that use vision that way, and we've done an awful lot that way. We have done an awful lot with radar antenna assembly and other applications for other companies that build radar antennas, and they all need vision and now really high-end vision. We've done some with profilometers and stuff where you're looking at surface roughness and characteristics of parts using that technology on top of vision in order to figure things out even more accurately, so that you could get things to go together right. We've used it a lot for inspections and stuff. We just finished a system where there was some crack identification and voids and all that stuff, and very, very small, fine components that were then going into an assembly. So, we built a system for the U.S. Mint years ago that assembled coins into the uncirculated coin set, and the objective there was to put the coins in this clear container, and all the heads had to be rotated up so that all the coins looked right. So the only way to do that was with the vision. And so, we automatically fed the coins, but we didn't bother trying to figure out rotational orientation until the robot was going to pick it. So your camera looks at it, figures out the orientation. The robot will make the offsetting moves before it places it. And in that particular system, the plastic case we were putting them in was a die-cut vacuum form thing that had very wide tolerances on position. So you couldn't corner crowd it in order to locate pocket geometry in order to put coins in, because they were press fit in, so it was a tight fit. You had to use vision to find the pockets. So I think we had 42 vision systems on that machine with 8-9 robots in order to figure everything out we needed to figure out in order to put coins in that package.
Wow, that's a lot of technical requirement in order to solve many would assume, well, how hard is it to put things into a tray?
Oh, and you got heads up and heads down. There's a whole set of vision systems to do heads up and heads up and heads down sorting in the feeding systems.
So, Bill, how do you find and grow technical talent with these capabilities in a specialized company like Edmund?
So, it's a pretty unique. So, when you're developing automation systems, we'll start with one requirement that you can't take. You got to be careful about the risks you take, about the stuff you're doing that's never been done before, because it's got to work. Because there's a lot more that goes to building a machine. Somebody's going to spend $1 million on this machine, and that little $50,000 piece over there has to work along with the other $950,000 that you spent on this thing, right? So you have to be careful what risks you take. And a lot of companies have built a lot of very helpful tools that we use to solve complex problems. Vision systems being a very good example. 6-axis robots, another good example. So we call it the automation toolkit. It's all the stuff, linear slides, servo slides, all the different sensors, uh, all the different safety products now that are available, how to do safety systems that meet safety standards. All those different things someone has to learn in order to really contribute in designing and building an automated system. And if you don't find someone who's experienced at it, who's worked at a competitor, right, then you've got to teach them those things. So we tend to hire, recruit, looking for people that we think have the skills to learn all this stuff, and then we teach them the stuff. And so there's a decent learning curve and time frame. So the mentoring is a really important piece of how we run our business, so that we've got experienced guys who know what they're doing, and um, and their one of their jobs is to mentor the guys who are learning, and to make sure that and to review the stuff that's being done, um, so that we try and catch before we machine metal, not after, or buy parts, potential downfalls or pitfalls or issues in a design. So there's the mentoring piece. There's making sure that the person who's new working on something knows who the experienced person is, who's probably the best mentor for that job. And then making sure that there's reviews done on it as a team, both with the customer and internally, so that what we decide to build, we think has the best shot of work.
Yeah. Minimize the risk, as you mentioned. And Bill, what are some of the lessons that you've learned about leading engineers and technical innovators?
Okay, one of them I will say is that not everyone is cut out for it, and it's hard to figure that out in the interviewing process. And so there's definitely it's like with anything else, there's a certain you as much as you think that once you've taken the time to review and hire somebody and you started doing the training, that doesn't mean that they're going to make it. And so sometimes you have we do frequent reviews of how people are doing in progress, and sometimes we have to, sometimes they don't make it, and you have to recognize that that's all part of the process.
There's a lot of demands from your customers, and you need to be able to meet them so that you have more and more customers.
Yes. Oh, yes. So I've had to, in my career, so Advent, we're talking about what Advent does today and what Advent did when we started, but we did a lot of other things in the middle. And so I've had the opportunity to build and mentor and this team, and do other things. And so so over time, I mean, a few of the guys have been with us now starting 30 years ago. You know, I had a couple of guys who I had on the, initial people that we hired when I was young, a lot younger. I wasn't as smart about all this stuff. So I made a lot more mistakes and hired people who really shouldn't have stayed on, and didn't do a lot of enough of the things that we're talking about today that we do today, that make us a better organization. And so we had a lot of, stuff we went through, and one of them was hiring somebody, promoting him to be a automation manager, and then nobody liked working for him. So all of a sudden my team disappeared, and all it is me and him. And I'm like, this isn't working. Okay. So it's not me and him anymore. He's gone. And unfortunately he was great at it. He was a great automation engineer. He really was, but man, he was a horrible manager. So I had to, learn that the hard way.
How do you balance being a technical leader with all the demands of being the CEO of your organization?
You know, the way I do it today is very different from the way I used to do it, and I've learned that I have to delegate responsibility, and I have to accept the fact that they may do it differently than I would have done it, or they, or that I'm not sure the way they're going to do it. I won't say isn't going to work, because if there's a technical difference of opinion about something, we have to come to a meeting of the minds. But if there's a something else about the way they're doing it, I've learned to give my team a lot more responsibility and latitude to do things the way they think it should be done, and then a lot of times we'll do it not just a team but a company wide lessons learned, and so we all talk about what went right, what went wrong, and it's not just me trying to influence how it's going to be done differently the next time. Actually, most of the time, it's the rest of the team, and that's a lot more powerful when your peers have opinions about things. A lot of times,
Yeah, and then they own the results. They're not just receiving information.
yeah. So today, quite frankly, I've got in place a really good management, a set of managers, project managers, technical managers, group managers for technicians and machine shop. And so I let them pretty much run with the ball these days, because I know their strengths and weaknesses, what they're doing, that kind of stuff. And I'll look over somebody's shoulder if I'm concerned about something technical, or I ask somebody to do it. But I get to pick and choose what things I work on now. So I'm a plug. I plug holes. Somebody needs to do this over here. I'll take that. Or and I do a lot working with customers on developing new ideas and new concepts for solving problems. So I get the luxury of stepping in on the front end of things, and that's probably what I do best now, because I've been doing it long enough.
Yeah, you've seen enough to know where the road ends.
I've seen enough.
Exactly. So in general, though, what would you say continuous improvement looks like in your world? Not just lean thinking, but overall systems and processes and who does what and when.
So we do actually have a pretty robust continuous improvement data collection system at Advent. We actually built it when Advent was doing lots of other activities. We had two companies under Advent. We had a company that built test equipment for utility metering. When I started Advent, I had a partner. He and I split in 2020, and I took the part that just does the custom automation. He took the part essentially that did the utility test equipment business, which was 85% of our business at the time. So that company today has about 250 employees. He's doing 50, 60 million in sales. So that was the primary driver. It was what was happening inside of that company that was the primary driver of most of the systems we built. So I got to build these systems as a combined entity, and then I took all those systems and we use them today because they really provide a good structure for us to grow. And our continuous improvement system was one of the things that I took. And it's something where people put in suggestions, ideas about things that could have been done better or whatever. We collect that information. We keep track of how we act on it. We report it back to the person who reported it. So it does really promote, because we do keep track of all the ideas that come in and all the suggestions and all the things that went wrong. And we document how we got to resolutions on these things. And so the employees see that there was a benefit to it because somebody actually paid attention to it.
That's very valuable. There's no point in collecting things if you don't do anything with it.
Yeah, if you're going to sit there. Yep.
So along that, how do you encourage a culture of experimentation and iteration in your teams?
The guys see it pretty quickly. There's been two or three. I talked about the brace shaping project and the machining, and the guys who were involved in that project saw pretty quickly the benefit of saying, of isolating an issue and then chasing it down from a design and experimentation perspective to get something that works right. But we just okay. So we're building a system right now that is a rain and wind testing machine for roofing materials. Okay, so it's a big blower. It's all these rain nozzles. It's water detection, a leak detection thing that goes under the roof, and all that goes into a control system. And one of the things that we weren't sure how we were going to execute was actually how to distribute the water in a rain tight fashion on the roof in this experimental thing. And so we had a few ideas about how to do it. There was a way we did it before that wasn't really going to work this time. So we had some initial ideas, but we took PVC pipe, drilled holes in it, put water on it, measured flow and pressure and stuff, and basically built test rigs to figure out how best to distribute the rain. And it seemed kind of like, do we really need to do this? But I got to tell you something. There was quite a bit of hardware in the rain delivery system in that machine, and part of it had to work when the wind was off. Part of it had to work when the wind was at 45 mile an hour, and water flow coming down on something. I'll tell you. So when we ran the test at 45 mile an hour, it went this way. And fortunately, the system worked because we had rain jets that were in the flow. So those get turned on when you're at 45 mile an hour. These get turned on when it's at 0. And it was actually, as executed, a fairly simple system, but there were a lot of details to it that made it work in all the different scenarios that this had to work in. And it worked the first time. And I think that's really where people see the benefit of the thinking and the experimentation that goes into making sure that the pieces of the machine you're not sure about work right, is when you did all that and it worked the first time. And that's happened recently on 2 or 3 different projects that had difficult pockets in them. And so the guy, and I see it because the machine gets built, turned on, and it works first time through, and you're like, son of a bitch, that was nice. And it works on many levels. It's, we're not trying to fix the machine to make it work right. We're not spending extra time and telling the customer, oh, we made a mistake, we got to fix it. We'll do it. We know what we're doing, but we're not done yet, and we're supposed to be. That's another aspect. And then there's the cost aspect. We estimated how much it was going to be. We estimated that we were going to do this testing. It worked the first time, so we didn't have to redo anything. And then from a cost and profitability perspective, we've met our objectives. So we see it in each of those different areas. And the guys see the results on all those areas too, and it has a tremendous impact.
And the happy customer at the end of it all.
Yes, absolutely.
They got what they asked for, and it works properly, and there's no oopsies. So, Bill, thank you so much for all your insights. And in closing, I like to ask the question to all our guests of and for you, it'll be automation in general and all the great, wonderful things out there and the new technologies that can be taken advantage of, and all the automation possibilities in products and services and processes in general. What do you see the future of automation as a whole for the manufacturing industry?
I think we'll continue to see an evolution of automation, and it's mechanical. How it's done mechanically, how the controls are done, how the software. Those are the 3 main groups, right? Mechanical is all the stuff that does the actual touching and manipulating and stuff, and then the controls are the piece that puts the software or allows the software to get its job done. But you're seeing so many things happen on the software world with AI. And, we've just seen it start to touch vision. But we haven't really seen it touch anything else yet in our world. Now, remember, our world is much more, it's got to work. It's got to work within specifications, and it's got to work for a long time. So AI has been envisioned for a few years now, and we resisted committing to it on a project because when you commit to something on a project, you have to know that it's going to work. And if you're training it to do a bunch of stuff and then it's supposed to figure stuff out and you don't really know how it's going to work, how do you make a commitment around a machine that's got all this other stuff going on? So the evolution of that stuff in our world is going to take a lot more time as we have opportunities to see how it can help us and we understand how it works. But it will have an impact in our world and how we do things and what we can do and the more complex tasks that can be done effectively. You see it in automated driving. Okay, I have a Tesla. I love the damn thing, and I've seen their automated driving package evolve over the last 4.5 years since I've had the car, from something that was pretty crude to something that is pretty intuitive, and I think we're going to have an opportunity to see how that all evolves in our world. But like I said, it's going to take a while, but it's going to open up even more all the things that we can do with devices to make products.
Yeah, don't they say like a journey isn't just about reaching your destination, it's about all the experiences you have along the way of getting there?
That's right. That's exactly right. And we still have a ton to learn in that realm, and what benefits it can provide, especially when the bin picking is a great example, and people spend a lot of money trying to perfect it and to develop vision systems that can see things well enough, and maybe not just vision, but also other types of sensors that gives you the flexibility to be as intuitive as a person is, to do something as simple as picking a piece out of a bin, which is really hard with an automated system. But there's a lot of hype around that application, and boy, once we get it figured out, there's a lot more things that are going to be more cost effectively automatable. And what's interesting there is that when it's the software, the replication cost is the development cost is infinite and replication cost is zero. You know what I mean? So it's the type of technology that has an opportunity to really change things, to change the ROI on something, because depending upon how prevalent it becomes and how easy it is to use it in different applications.
I totally agree. And those bin picking stuff, when you figure it out, let me know. I have hundreds of applications to start looking at, because that's the number one challenge is, okay, I can put it together, but I still need someone to put it into a slot. And then what's the point of automating it if the person has to pick it up anyways? Okay, so let's just automate putting the screw in, and we'll just use a screw bench. And it comes down and puts the 4 screws in at one shot in 12 seconds. And that's where most of it is at still. But once you figure out that AI vision to see shapes and pick it up in an intuitive way, that is a problem worth solving.
Yep. So we're all patiently waiting.
Oh, I can't wait. Well, thank you so much, Bill. We really appreciate you being a guest on our podcast. We invite all of our followers to follow us on YouTube and on Spotify. Thank you all for listening, and please do share. There'll be more episodes coming. And again, thank you, Bill, for being a great contributor to our podcast.
I appreciate the opportunity. Thanks for having me on.